next speaker is Dr. Lakey. Dr. Jonathan Lakey is a world-renowned researcher at the University of California Irvine. I'm here in Irvine. This groundbreaking research he does to find a diabetes cure has been widely published in nearly 500 scientific papers. He recently published a book on his innovative improvements in islet isolation. Numerous research grants and awards from prestigious global organizations such as the Alberta Heritage Foundation, Canadian Diabetes Association, JDF International, and he told me Lions of Canada has helped him. So he has helped fuel his revolutionary work in stem cell and islet cell transplantation. Dr. Lakey will talk to us today about the recent improvements of islet isolation techniques and the development of the Edmonton Protocol for patients with type 1 diabetes. So Dr. Lakey, thank you so much for joining us, and it's all yours.
Thank you very much, Brian. Can everybody hear me?
Yes.
Great. I'm going to share my screen and start my PowerPoint. I'm joining you this morning in an airport lounge in Vancouver, Canada. So I apologize for that. So as Brian mentioned, I'm a professor of surgery and biomedical engineering, also the director of the Clinical Islet Program at the University of California Irvine. And I'm going to be speaking to you today on the treatment of diabetes using cellular therapies. So as Brian mentioned earlier, and as I mentioned in my lectures, I always introduce my talks talking about the Canadian team of Banting, Best, McLeod, and Collop, who 100 years ago really discovered the discovery of insulin, and unfortunately, exogenous insulin therapy still remains the basic treatment for patients with type 1 diabetes. So the epidemic of diabetes, in 1985, there were approximately 30 million individuals. The numbers just continue to increase with projections of 500 million people by 2030. So it is an epidemic. We need to start working on ways to solve this disease. And my lecture is going to focus on cell therapies, including using human islet cells, but also some of the future work using stem cells and stem cell derived products. So the methods of delivering treatments of diabetes include injections of insulins, and you take a look at these two young boys. When people say that insulin is a cure for diabetes, I show them these types of slides, which illustrate the number of insulin injections over a month-long period, either with the individual insulin injectors or with the continuous glucose monitoring systems. There are interests in inhaled insulin and also insulin pumps with a continuous feedback system using the continuous glucose monitors, and there are several companies that are doing a lot of work in that field. My focus has been in the field of islet cell transplantation, isolating these insulin producing cells from the pancreas and then transplanting them into the individuals with brittle type 1 diabetes. So beta cell therapy can be accomplished in two ways. There are whole pancreas transplants, again, relying on organs from cadaveric organ donors, where they take the pancreas, as usually at the same time they're doing a kidney transplant, and they transplant that into the diabetic patient. This is a major surgical procedure. Patients are in the operating room for 6 to 10 hours. They're in the ICU. They're in hospital for usually a week to 10 days. A much simpler approach is to focus on these insulin-producing cells found within the pancreas, isolating these islets of Langerhans, and then infusing them into the liver of these patients, where they float up in the sinusoid of the liver, where they start to secrete insulin. It's done under local anesthesia, and not in an operating room, but in a radiology suite, and the patients usually go home the next day. Here's, in fact, one of our very first patients in Edmonton, receiving an islet cell transplant. He's awake. We just go in through a small cannulation into the liver and monitor these patients while they're talking to us and infusing the islets. The islets, the cannula is going into the liver. Here you can see the cannula entering into the portal vein, where we draw the islets up into a syringe. This is very early on with James Shapiro and myself, drawing the islets into a syringe, and then those are injected into the patients. As I said, it's not done in an operating room. It's done in the ultrasound with fluoroscopy and X-ray. It takes about 15 minutes to access the portal vein, the big vein that runs from the body through the liver. And again, we stopped insulin therapy right away in the radiology suite and only return to insulin therapy if they need it, if their blood sugars rise above specific levels. So we published our first paper in the New England Journal of Medicine outlining the details of what was later termed the Edmonton Protocol. It involved improved methods of islet isolation and characterizing the islets. It also involved development of a potent steroid-free immunosuppression protocol. Prior to the Edmonton Protocol, patients were placed on steroids, and we knew that steroids not only inhibit insulin secretion, but also prevent the insulin from being utilized in these patients. So James came up with a novel protocol that included 2 new anti-inflammatory drugs as well as immunosuppressants. And again, we were able to see insulin independence in the first 7 patients that we transplanted using this novel protocol, which required the use of cadaveric organ donors. This slide illustrates before transplant, patients are measuring their blood sugar, and I apologize, the blood sugar on the left side versus time of the day on a 24-hour clock. This is the average number of blood glucose readings taken over a 1-month period. We'd like to see the blood sugars between the red and the blue line. And unfortunately, we see a lot of hyper or high blood sugars, but we see these dangerously low blood sugar readings. People are measuring their sugars throughout the day. There's only a very short time frame when they're actually sleeping and not having to get up and measure their blood sugar. This is all done prior to the transplant. After the transplant, they continue to measure their blood sugar, and this is the type of blood sugar control that we can see once we transplant sufficient number of islets into the patient. We have resolved the hypo blood sugars, and we see very few higher than normal blood sugar readings, and those typically are right after meals. So this is typical of what we see in patients after islet cell transplantation. When we look at the hemoglobin A1C, which is a marker of blood sugar control over the past 3 months, pre-transplant, on average, they're about 8.5%. After transplant, within a couple of months, usually about 3 months, the blood sugar comes down to now close to near normal, upper levels of normal range, and stay so as they follow out for months and years post-islet cell transplantation. If we look at the rate of insulin independence versus the months post-transplant, and for this slide, we combined results from our program in Edmonton with a group in Miami and Minnesota. We're able to see at 1 month about 80%, or 8 out of every 10 patients were able to maintain complete insulin independence at 1 year post-transplant. What happens over time, unfortunately, is you're getting a loss of beta cells. They're being stressed. There could be some toxicity to immunosuppressants, and that rate falls to about 1 in 10 after 5 years post-transplant. After the first paper published in the New England Journal of Medicine, we received support from the NIH and the Immune Tolerance Network to replicate the Edmonton Protocol in 9 islet transplant centers around the world. And in 2006, we published another paper in the New England Journal of Medicine of the international trial of the Edmonton Protocol for islet cell transplantation. So at that time, President Clinton hailed the Edmonton Protocol as a major advance in the treatment of diabetes. So since that time, there have now been over 65 institutions and over 2,500 patients around the world that have received the Edmonton Protocol or variations of the Edmonton Protocol based on our willingness to share the protocol, to work with teams around the world to help those patients with diabetes. So where do we stand today? Islet cell transplantation exists today but it's limited in availability and supply because of the limitations in organ donors. The variable quality of organ donors also impact our ability to collect enough islet cells for clinical transplantation. These patients all require chronic, lifelong immunosuppression on immunosuppressant drugs. And a BLA or a license to do this in the United States has been pending for a number of years, and it's very limited. There are, however, countries, Canada, England, Switzerland, have their federal governments have all approved islet cell transplantation. So we're hoping that it continues to move forward. We're hoping to increase the rate of organ donation so that we can help those patients with diabetes. However, if you look at the two issues limiting this therapy, it's the unlimited source of insulin producing cells, and it's the lifelong immunosuppression. And this handful of pills represents what a patient has to take after islet cell transplantation. So our goal is to come up with an unlimited source of islet cells that may be xenogenic, meaning it's going to come from an animal source. Pigs have been given a lot of research efforts, or from stem cells, and stem cells that can be used to differentiate into insulin producing cells. The other goal is to eliminate the need for lifelong immunosuppression. And our work and work by many other groups have been focusing on taking that and encapsulating or putting those cells, either the islet cells or the stem cells, into biomaterials to prevent them from being destroyed by the body. So this just illustrates some of the groups that we're working on, groups in Canada, the United States, and Argentina, Australia, China, even in Korea, where we're working on trying to address those two critical issues to try and actually come up with what we can actually believe is a cure for diabetes. So in terms of the biomaterials, what we're doing is we're taking these insulin producing cells, we're putting them into a biomaterial matrix, and some of the key challenges are making sure that there's enough blood going in and nutrients going into these cells so that they survive. And that has to do with the biomaterials we're using, making sure that they're biocompatible, developing ways to monitor the survival of those islets. And in some cases, we're looking at ways where you can take those cells and replace them, just like you go for an oil change for your car. So at UC Irvine, we've developed a method where we use purified alginate. Why alginate? Because it's a biomaterial that is inert to the body. We have purified alginates that we collect from the seaweed, we purify it, we can put it into the body, and the body doesn't recognize it as foreign. We've developed a system using an electrostatic generator where we take islet cells in a liquid, we run it through a very high voltage, and then we drop it into this solution that contains calcium, and the calcium causes that liquid alginate to then form into a capsule. So we can make these capsules, and over here is a capsule of alginate with this islet cell in the middle, and with chemistry we can adjust the pore size of that capsule. So you're looking at a 3D ball, but this is about 200 microns in diameter, and so we can allow and change the porosity to allow nutrients like insulin, glucose, oxygen to move through this capsule membrane, but block things that are involved in the immune system like antibodies. So it's a delicate balance of making the capsules and then having them so that they protect the cells from destruction by the body. So when we take animals, we can make animals diabetic. There's drugs. This was one of the drugs that we use. We make an animal diabetic. We monitor him. He becomes hyperglycemic. We can then transplant these encapsulated islets without any immunosuppression into these animals. They take about a week to 2 weeks to come and become normal glycemic. And then we can hold them out for months and months and months, again, without any immunosuppression. So why aren't we doing this clinically? Well, because the number of cells that we require is really a lot to cure a mouse, and to do a human would really be counterproductive. So how are we going to get to the next step? So we've been working on stem cells, and that was one of the reasons I moved to California, was to work at the Sue and Bill Gross Stem Cell Center at the University of California Irvine, where we have a facility that's been built all for the focus of stem cells. So a stem cell is a cell that can renew, it can differentiate, and it can specialize. So if you think of the stem cell as a seed of a tree, it can be pushed down different avenues or different branches. So for developing a pancreas or an islet cells, we can go down the pathway or the branch to become endoderm cells, and then pancreatic endoderm, and then endoderm cells, and then we can have our insulin producing cells. So there's been a lot of people that have been working on how do you get cells going down these specific pathways. So there's researchers working on various aspects of neurodegenerative disorders, bone, but our focus has always been with the pancreas to develop these insulin producing cells. So Doug Melton is a Harvard researcher. He published a paper a number of years ago, really detailing the steps that are involved to take a human pluripotent stem cell and push it down that pathway then it becomes a insulin producing cell. And it's all done by trial and error, trying a specific chemical. If it works, then you go down that path. So there's about 7 very distinct markers that take us from the stem cell down to that differentiated cell. We've also been working on human umbilical cord derived mesenchymal stem cells, or MSCs. And mesenchymal stem cells, again, have that capacity to be used in our example with our biomaterial to be able to protect those cells from destruction. So we collect the umbilical cord after the baby is born, screened, just like we screen for organ donors. We collect that umbilical cord, we culture those cells, and we collect what those stem cells, those mesenchymal stem cells, are producing, which are called exosomes. And we are using those exosomes in our biomaterials. Again, from one cord, we can isolate over 100,000 units that we would use for a clinical transplant. So we can treat 100,000 patients from those stem cells from that umbilical cord, which is typically discarded after the baby is born. So when we've taken these exosomes and embed them into our alginate capsules that I talked about before and put them into animal models, we can take a mouse after 28 days and we'll be able to collect those capsules, and you can see them here, and then we stain them for very specific markers that tell us about inflammation and fibrosis and overgrowth. And you can see this is work done by one of my students. You're able to really prevent any fibrotic overgrowth if you put these exosomes within the islets. So the next step was to say, okay, now let's do a transplant. Let's do a transplant of islet cells into this mouse model of diabetes. In one group, we will add just the alginate. In the second group, we'll add the alginate, but we'll put some exosomes into these mice and we'll monitor them. Again, none of the animals received any immunosuppression. So this is what happens, and this work was published just about 6 months ago in Nature Communications, where we made the animals diabetic with these drugs. We transplanted them. The animals in red were the control animals that they just had islet cells with no membrane or no protective membrane, and they all rejected and became hyperglycemic within about a month. If we took the animals that received the islet cells embedded into the alginate capsule, they became normal glycemic. They went out about a couple months, and then they slowly became diabetic. So they failed at about 2 months. However, if we took the islet cells embedded in the alginate with exosomes, and in green, we showed they became normal glycemic. They stayed normal glycemic. At 100 days, we took some of the capsules out of a few of the mice, and those mice all became diabetic. So that confirmed that the blood glucose control that these animals were receiving was due to the transplanted islets. The remaining animals in the study, we kept going for 6 months. So we had 6 months of function in these animals without any immunosuppression using the islet cells and the exosomes embedded into our biomaterial. So what are our next steps? We're further looking at how we can modulate these mesenchymal stem cells and really optimize their anti-inflammatory effects. We're also utilizing now stem cells that have been differentiated into insulin-producing cells in animal models of diabetes, and that's done in collaboration with a company called Pancreas, which is a spin-off of Novo Nordisk, the largest insulin manufacturer in the world. And then our goal is to validate these small animal observation in a large animal model of diabetes with a goal of transplanting these cells into patients with type 1 diabetes in 2023. So in terms of acknowledgements, I acknowledge the team at the Department of Surgery, Department of Biomedical Engineering, the staff that supports a lot of our research at the Sue and Bill Gross Stem Cell Center, collaborators in Irvine, including Children's Hospital, the Hoag Diabetes Center, with funding from a variety of sources, including the NIH, Juvenile Diabetes Foundation, California Institutes of Regenerative Medicine, and Padre Foundation that helps support some of our work. Thank you very much, and thanks for the opportunity to speak to you today.